Welcome back. This is week 6 of inverse methods in heat transfer. We are going to review basic probability theory in this series of videos in week 6. And we will apply this basic probability theory to some probabilistic methods in week 7. Now, so far, the methods that we saw were methods that were inverse methods that utilized some functional fit. So a functional model, the functional model is something like t hat equal to w0 plus w1x, or quadratic or exponential, etc., etc. So these models were either linear or non-linear. And we saw that we needed different approaches to solve for linear or non-linear models. Now, within that, you would have seen a subtle thing. You might remember that we had our weighted linear regression, where we saw that not all data points of which we were doing the inverse were weighted equally. Now, here I had introduced some term sigma, which was basically the uncertainty in measuring the temperature of the thermocouples, measuring the uncertainty in the measurement made by the thermocouples. Now, this is what is going to be extended within this week and the next week. The idea is we actually account for the fact that there is uncertainty in measurement. Okay, so this I'm going to talk about a little bit further. But there are different sources of uncertainty. And it turns out there is a powerful series of methods which arise from probability that handle this uncertainty. In fact, we will see that the probability method is actually a superset. Okay, so probability methods in some sense are more powerful than the functional methods. We will see next week that all the methods we derived so far can actually be derived from the viewpoint of probability. Of course, this is a really, really deep subject, as is, of course, probability theory. So really speaking, we should spend about 40 to 50, 60 hours just reviewing probability theory and basic statistics. We don't have the time to do that. We'll just spend an hour or two. I am assuming that you're already familiar with basic counting probability, though I will review it and we'll have one or two such review questions in the assignment. But the purpose here is just a review and not really a full-blown theory. I will try to make this compact so that you can utilize these insights within the next week when we come to some Bayesian techniques and Markov chain, Monte Carlo, etc. A few inverse techniques that have proven to be extremely powerful in practice. This is just a basic introduction. Once again, I am just re-emphasizing this. The purpose of this, in case you find this a little bit doubtful or a little bit confusing, please ask questions within the forum and we'll be happy to answer that. So let's go forward and just review some basic probability theory for this week. So what is probability? Probability, as all of you know, is just a mathematical framework for representing uncertainty. As I said a little bit before, the reason we are looking for probability within inverse methods is it actually gives us multiple ways of handling the inherent uncertainty in physics, especially in inverse problems. Remember that inverse problems deal with a series of measurements and we want to find out the inherent cause for these measurements. Again, I'll go back to the example we looked at. Let's say we have a fin, we have a whole bunch of thermocouples, we measure the temperature and we want to find out what was the heat transfer here. Okay, so this is the cause and this is the effect. Now, of course, there are a whole bunch of sources of this uncertainty in physics. For example, you could start right at inherent randomness in the system. For example, you could start with quantum fluctuations or fluctuations in outside temperature, T infinity. Okay, so there could be a little bit of randomness in the system in the boundary conditions. So that's one place. Another source of uncertainty is you could have incomplete data. Okay. So for example, here we actually don't have temperature measurements everywhere. We only have them at a few places. And even within that, so you have made partial observations, or you might have made errors in the measurement of the thermocouples. So for example, any observation. So if you are dealing with MRI, there could be noise in your detector. You could have a whole bunch of series of problems in how you made the measurement itself. Then finally, you could be modeling the problem incompletely. For example, we have been modeling our convenient slab problem as if it is 1D. But really speaking, the problem is three-dimensional. Again, we assume that all the dimensions are the same, but this could be wrong. Or more seriously, the modeling itself is incomplete in that even if you apply a full 3D law and you put geometric certainties and you don't have any inherent randomness in the system, you still can't model it because you don't have sufficient resolution. So that's where things like turbulence models, when you have turbulent heat transfer, etc., all these things come in. So there are multiple sources of uncertainty, and we are going to club those together within this one huge thing of saying there is some uncertainty in the system. Let's put that together and talk about probabilities. And also remember, this is extremely useful for ill-posed problems. Because as you know, the same measurements as we saw within our function fit could be drawn or could be created by multiple inherent models. Okay, so we saw that briefly during overfitting also. So all that, which model it is, how accurate the model is, how accurate is the data, all these uncertainties put together come into this one big picture of probability. And so this is where probability theory is useful in inverse methods. Now, there are two ways in which we use probability ideas within inverse problems. This is also true of machine learning, as we will see later in the next 3-4 weeks. From week 8 to week 10 or week 8 to week 11, we will be looking at machine learning methods. So you will see that there is a very close relationship between inverse problems and machine learning, which is why we have included that within this course. So the first use of probability ideas is within constructing models. Okay. So the idea is, remember the models that we constructed so far were, well, I'll assume there is a function which fits this data in a least square sense. So this is the functional approach. Now, instead of that, we are going to do something else. We are going to say there is a probability distribution function. I'll explain what this is in case you are not familiar with it. I'll explain what this is within this video itself. At least we'll take a first step. Now, this is a slightly different approach. What turns out is the function approach is a special case of the probability distribution function. In fact, you can show that in some sense, the mean of this probabilistic distribution is what appears as the function in what we looked at in the last 4 or 5 weeks. Okay. So one way in which we use probability theory is to construct or to make such models and then use them for inverse analysis. The other way in which you can use probability ideas is even if you use deterministic learning systems or deterministic models, they are only correct part of the time. So for example, you might remember goodness of fit. How good is the fit? We will see something else called correlation coefficient later on this week. So all these ideas are statistical ideas. So they are useful in analyzing models. So even when we come to machine learning, we'll see that to analyze, to tell you how good our model is, we still need a probabilistic idea. So that some other model could have fit this data, even if it's a deterministic model. So the model could be, so probability can be used to make a model or to compare existing models. Okay, so we'll be using this theory in both these ways. Okay, so please notice this in making models as well as analysis. So these are the dual uses of probability which we'll be using within this course. Within probability theory, there are two different philosophies. Okay, I'm not going to go too much into the philosophy. In fact, we are going to almost eliminate it other than this brief discussion. However, since it's a frequent discussion, it makes sense to just address it here. There is something called the frequentist approach, and there is, of course, the Bayesian approach. Bayesian approach is what we are going to be using, and it's particularly useful, in fact, for inverse problems. Okay, you will see it's almost impossible not to take a Bayesian approach to inverse problems, which is why I'm addressing this. Frequentist is usually the method that we have seen. So, for example, if you say something like there's a 60% chance of rain tomorrow, okay, then there are two interpretations. The frequentist approach is that you assume an infinite sample space. I'll define what a sample space is later in this very video. But what you assume is, let's say you have a coin and you're tossing a coin, and you assume that if I toss the coin infinite number of times, then half of those will be heads and half of those will be tails. So the next time I toss the coin, I'll say there's a 50% chance of getting a heads. So this talks about some objective measure, but the objective measure, of course, depends on some thing which is not really realizable, in that you can never do it in practice, but you can see it on the computer. That's one advantage of doing coding, which we will see next week. That you can actually start seeing it slowly converge to 0.5, the number of heads. But if I toss a coin 10 times, I might not exactly see 5 heads and 5 tails. What I'll usually see is something like 3 heads and 7 tails, or 7 heads and 3 tails. And we will see how to deal with this inherent uncertainty within. I mean, this is sort of a meta uncertainty, uncertainty within uncertainty, that we'll see later. But what the frequentist approach says is that whenever I say 60% chance of rain, it means assume you are going to live in a universe which splits, or in a multiverse, and it splits into infinite universes. And out of all those universes, in 60% of those universes, you're going to have rain. And this is sort of an objective measure. Now, there are strong people who believe in this. In fact, the whole school of quantum mechanics, in fact, some of you might have heard of quantum computation, that strongly depends on this frequentist approach. Okay, it strongly depends on assuming that there is some such objective measure of how things happen. Okay, and we actually have technology that uses this. On the other hand, we have the parallel assumption of what is known as a Bayesian. So this measures a degree of belief. So in the sense that it's a degree of belief, it's subjective. So you might say something like, I did well in the exam, so I think there is a 90% chance that I'll get more than 15 marks. Okay, but nobody has actually done the experiment infinite number of times. This is just your degree of belief. Or when you say 60% chance of rain, it is a rough estimate of saying, well, I am not 50-50 sure. I think there is more chance of rain than not. So I am kind of estimating. Now, you might think that this is vague, but it turns out this is very, very, very powerful, because we have an objective theorem coming out of this subjective idea, which is known as Bayes' theorem. We'll prove that. You would have anyway seen that in school and early in college, but we'll prove that later on this week also. This is, as I said before, this is almost indispensable for inverse methods. Why is that? Because when I say something like find out the thermal conductivity given a whole bunch of temperature measurements, and if I give a particular material, I actually have an idea of what the thermal conductivity will look like. Similarly, if I ask you to estimate, how much will be the rainfall in Chennai, you have an idea that it is not going to be 1,000 kilometers. So you have a subjective idea of how much the range is going to be. In such cases, this is called a prior, and you can incorporate that. This subjective belief can be incorporated back. And there has been a lot of debate over the centuries, and especially over the last century, about which view of probability is correct, because in some sense, towards the end, it has some subtle differences on how we calculate probabilities. But as far as we are concerned, within this course, the probability, the way in which the mathematics of probabilities works the same way within our limited context. We are not doing quantum mechanics. So if we have something like the probability of disease 1 is 0.1 and the probability of disease 2 is 0.2, then probability of disease 1 and disease 2 is the multiplication of these two probabilities if they are independent, regardless of whether you take a frequentist approach or a Bayesian approach. So we will stop talking about these philosophies and primarily take, as we go ahead, especially during the next week, a Bayesian approach. And that will be subtle. It will be behind the scenes. It's not going to be something that we explicitly talk about. Of course, we use Bayes' theorem, but that's not only the deal with Bayesian probability. In case you're interested in this kind of debate, I would recommend that you read some basic books on that. There is an excellent book which supports the Bayesian approach by E.T. Jaynes. It's an old book. It's a really, really good book if you want to think about such philosophy. So we are going to end the philosophical debate here and move on to actual definitions of what probability means and what the various quantities that we are interested in are. So the definitions we are interested in, again, these are just so that we have some simple terms to talk about. The first one, the most important one when we deal with probability is what is called a random experiment. So literally the experiment that we run in heat transfer would be the example of a random experiment. So I take, so for example, the unsteady case that we looked at, we make multiple temperature measurements in time. Now, if I do the same experiment multiple times with the same condition, so for example, the simple examples I have given here, you take a coin, it looks like okay, I've kept it at the same place in your thumb, when you're tossing it up, suddenly, sometimes it results in heads, sometimes in tails. Now, you might argue this is due to micro conditions or something of that sort, but that apart, from a macroscopic perspective, it looks like we have set as similar situations as possible and we are getting different results. Throwing of a dice, rainfall amount, or thermocouple measurement. So I keep the same slab and I put a thermocouple at a particular point. This is not going to give you the same measurement each time. You would have done this in school. Use the vernier to measure the diameter of a marble, something of that sort, and measure it multiple times. Each time you get slightly different results. Such an experiment, which seems to result in slightly different answers each time or different answers each time, is called a random experiment. Okay, so please remember this term, random experiment. Okay. Now, the second important term is what is known as a sample space. So this is basically the set of all possible outcomes of a random experiment. So in some sense, the experiment is sampling out of this entire space. Okay, a space has a whole bunch of things, a whole bunch of possibilities. Imagine this is a bag, you are pulling stuff out. So for example, the tossing bag has a sample space which has a heads or a tails, and you're putting your hand in and picking out either head or a tail. The thermocouple bag is a continuous bag. Okay, it has a whole bunch of possibilities, but even here there will be a range. Okay, so the temperature within a slab with some, let's say, 10 degrees on one end and 50 degrees on another end is not going to turn out to be 3000 degrees Celsius. It's not going to happen somewhere on Earth in a simple situation. Okay. Similarly, on the sun, you don't expect if the sample space will have high temperatures and it won't have suddenly minus 20 degrees centigrade. Okay, so the sample space is where we pick out the possible outcomes of a random experiment. These could be discrete or these could be continuous. Okay, so diameter of a manufactured pipe. So how we choose the sample space depends on the purpose of the analysis. This is not particularly relevant here, but let's say you are choosing something like the diameter of a manufactured pipe. You will say the sample space is the set of all positive integers. Or you could say that if you are only interested in finding out whether it's a low or medium or a high diameter pipe, you will choose the sample space as discrete. This is a continuous sample space. And this is a discrete sample space. Okay, or a satisfactory or unsatisfactory. Similarly, for temperature, you could say all positive values in case we are measuring the temperature in Kelvin, or we could say low temperature, medium temperature, high temperature, or too cool, or too hot, or satisfactory thermal conditions, or unsatisfactory thermal conditions in case you are doing some HVAC design. Now let's come to what constitutes the main thing in a sample space, and this is what we're interested in. These are random variables. Within inverse heat transfer and generally in engineering and science, we deal with numbers. Okay. So random variable is, instead of saying heads or tails, we would actually want to denote outcomes with an actual number. For example, if it's heads or tails, that's what is categorical outcome means, two categories. We can call it 0 or 1. Okay. The variable that associates a number with an outcome of a random experiment. So I take a slab, I make a measurement, and the variable that's going to associate a number is temperature. Okay. So the temperature is now a random variable. Now, I could also take a series of 6 temperatures and call it some capital T, which is made up of T1 through T6. This is also a random variable. Of course, it's a 6-dimensional or 6-component random variable. This will seem like a simple idea, but the notation often, whenever you read inverse methods literature, it can get a little bit messy, especially if you are not used to it. Okay, we are going to be a little bit casual about notation, but at least once during the course, I should mention it, because if you do a more advanced course on inverse methods, this will often become a bottleneck. So one of the purposes of this course was to make a somewhat accessible introduction to inverse methods. If you see textbooks, they often are very heavily filled with probability jargon, and they make it less accessible. So hopefully after you go through this course, if you're actually entering any formal inverse methods course in heat transfer or in any other subject, it will be a little bit more accessible. So let me make this a little bit more clear. So the random variable is typically denoted by a capital letter, okay? And its value is denoted by a small letter. So I'm going to take a simple example, and then I'll give you a heat transfer example also. So for example, I would say that the rainfall on a particular day is a random variable R. Okay, so R is the name of the variable. So remember, just like in a code, we have variables. So if you use C, you will say something like int or float R or double R. Okay, something of that sort, you would say. And R itself will take values. So for example, you will say R equal to 10. This I will denote by small r. We may say that is already capital R. R is the set of all possible values of small r. Okay. So that's what you should remember. Again, don't get too hung up on the notation. This is just so that in some of the slides I'm going to show right now, I'll be a little bit particular about the notation, and you might get confused on what capital and small are. Capital is the larger set, so to think, and small is the actual value it takes. So for example, if I ask what is the probability that the rainfall is greater than 10 mm, I will denote it by this notation. P R is greater than 10 equal to what? Okay. So for example, I could also ask what is the probability that the temperature at this point lies between 30 degrees and 50 degrees. Okay, so let's say this is 0.1. I would give something of this sort. Okay. I could also say probability that the temperature is equal to, this is actually wrong because you can't get a specific temperature, but temperature equal to, let's say, small t is something. Okay. We will come to this a little bit more carefully when we come to probability density functions. So I hope the idea itself is clear. Capital denotes the set of variables and small denotes the actual value that variable takes. Now, here is probably the most important idea that you should get at a conceptual, at a gut level when we deal with inverse problems. That is the idea of probability distributions. Now, the important idea here is that probability distributions tell us how likely a random variable is to take each of its possible states. Now, this might seem vague, but let me explain why this is important. Okay, usually we talk about probabilities of events. Individual probabilities are for events or outcomes from sample space. Okay. On the other hand, the probability distribution is for the entire sample space. How is it different? I might ask, what is the probability of a head? And you might say it is 0.4. Let's say it's a biased coin, and you might say it is 0.4. That tells me something, but in this case, because there are only two outcomes, I'll immediately know that the probability of tails is 0.6. So when I talk about probability distribution, I'm talking about the entire sample space. So imagine there's a sample space. All the possible events are here, and all of them sum up to 1. Right? All possible events sum up to 1. What probability distribution tells you is how is probability distributed within the sample space. Okay. Now, so remember, probability distribution corresponds to sample space, whereas probability corresponds to one event or a few events, whatever you are interested in. Why is this important? This is probably, in my opinion, the most central important idea as far as inverse methods are concerned. The idea of a distribution. Because it is not just enough for me in an inverse case to tell you, okay, heat transfer is 1500, okay, watts per meter square. If I ask you, how sure are you? Okay, then it actually makes sense for you to give the entire distribution. Why is that? Okay, so you want to know not only what the possible heat transfer is or what the most likely heat transfer is, you also want to know the entire range. Let us say the likelihood of lying between 1500 and 1510 is something like 10%. But there is actually a chance that you might hit 1700 watt per meter square. You want to know what that chance is. Is it 10%? Is it 5%? Is it less than 1 in a million? Because when you design equipment, you want to know not only one, or you want to know the maximum temperature. You'll say, okay, what is the maximum temperature within the slab? You might say, okay, 70 degrees centigrade. But maybe there is a small chance that it might hit 90 and it might conk off. Usually when design goes wrong, it goes wrong because we did not take care of the distribution and we looked only at the averages. So here is where the idea of a probability distribution becomes very, very powerful. You don't look at only one specific event. You look at all events in the sample space and you tell them, or you tell the person who is interested in finding out something about the system, the entire distribution. So remember this word distribution. People will keep on talking about it, whether you come to inverse or whether you come to machine learning, especially, people will keep on. So what is the distribution? What is the distribution? People want to know not only the specific event that you're interested in, but all the possibilities of all the events. So usually when we report the mean. Okay, what was your average score? So just imagine you are going to a college for admission and you tell them that my entire GPA or my percentage was 85%, but they want specific courses. They want to see what your full mark sheet, your full grade sheet. And if you go within further detail, how much did you score in each exam within each grade? So probability distribution has the entire information. So if you want to quantify the uncertainty of any event or any sort of experiment, all the uncertainties, the distribution has the entire information about it. So rather than asking for specific probabilities, you ask for the entire information if it is available. So sometimes it is not available and we'll see how to reconstruct it next week. That is our primary task as far as next week is concerned. But remember this, if nothing else from this week, please do ingrain this within your ideas that probability distribution is very important. Now, once you understand the idea of the probability distribution, you can immediately see that there are two possible ways in which this distribution could be done. One is it is discrete, that is the sample space has discrete separate points. So for example, this could be finite or it could be countably infinite. I'll explain what countably infinite is, so it's not particularly relevant. Finite is a number of typographical errors in a page. For example, how many errors I might have made, spelling errors, grammar errors within this page. How many are those? Okay. How many errors did a doctor make? How many times did it rain last month? All these are discrete random variables. All of you understand what discrete is. What I mean by countably infinite is how many stars are there in the universe. It could still appear like a random variable because we don't quite know the number, but it could be really, really large. There's no specific limit to it. But nonetheless, it is discrete. It's not 3.1. Okay. Whereas continuous random variables is where the sample space is like temperature. It has a real number interval. Okay. So for example, if I want the heat transfer, or if I want the temperature, I want the heat flux, I want the pressure, all these are continuous random variables. You could say temperature will vary somewhere between 10 to 30 degrees centigrade, but it will vary continuously. For example, within Chennai, it will vary somewhere between, in very, very rare occasions, like 7 degrees centigrade to, let's say, 48 to 50. It will not go above 55. It will not drop below 7. So that could be a range, but nonetheless, it's a continuous range. Okay, so in the case of a discrete random variable, you will measure probability distribution really as what is known as a probability mass function. Whereas in the case of a continuous random variable, you will measure probability by a probability density function. Now, we will not consider this too much, though I will introduce you to this in the next slide just for completion's sake. But this thing, PDF, so PDF is not our document PDF. It's a probability density function. It is a central idea. I cannot tell you how important it is. It's a central idea within inverse methods as well as machine learnings, and in machine learning as well as in general probability theory. Because most of the time, especially for our applications, we tend to deal with continuous variables. So, and usually for some reason, all of us find it a little bit confusing. Okay. So we will deal with this and you will see some deal of this confusion when we come to next week also. But hopefully we would have done enough background this week that it'll be clearer when we come to this next week. So discrete random variable versus continuous random variable. And if nothing else, remember this: continuous random variable and probability density function. So let's quickly come to the probability mass function, which is a little bit more intuitive. And then we will just use this intuition to figure out what a probability density function is. So probability mass function is just the list of all possible values along with their probability. So this is a simple idea. As I told you, you take the sample space. The sample space has a few events. In this case, let's say we are throwing up a dice, which has been manipulated and not all sides are equally likely. And you just list all their probabilities. This should have been probability of x equal to 2. So it throws up either a 1, 2, 3, 4, 5, 6. And the probabilities are written here. So to be a probability mass function for a random variable x, you need to satisfy a few things. Of course, remember the entire sample space has to be written down. And each individual probabilities, for example, if it reaches 1, 2, 3, 4, 5, 6, all of these probabilities have to be less than 1. That's kind of obvious. And the summation of all those possible probabilities should be exactly 1. Okay, so which is the case here. 0.6 plus 0.8 plus 0.1 plus 0.1. This is sigma p of x equal to xi equal to 1. Okay, over all I equal to 1 to 6. This is 1. This is the simple idea of a probability mass function. You could also draw it like this. So for example, x equal to 1, 2, 3, 4, 5, 6, and it will look like this. It will look like a point load: 0.1, 0.1, 0.2, 0.2, 0.2, 0.2. So this is the diagram of a probability mass function. Notice it cannot take any value between 1 and 2, 2 and 3, 3 and 4. This is where it differs from the idea of a probability density function. So the probability density function is what we will see next. But as I mentioned here, a probability mass function is like a point source. So you could think of, if you have done solid mechanics, you would have something like a point load, or within something like heat transfer, you could just have Q at a single point. All these are idealizations, but it works in a very similar way in that we simply sum up these things one by one and find out the net probability. Now, when we come to probability distributions, as I said, the more important or the more practical quantity for inverse methods in heat transfer is this idea of a probability density function. Okay. So this probability density function can work in multiple dimensions, which we'll come to actually next week, not really this week. But let's just assume this is in 1D. Okay. This is somewhat like probability per unit length. Unit length of what? Unit length of the sample space. Okay. So like I said, this is like a distributed source of probability. It is useful for you to imagine that there is the space and a whole bunch of infinite events are happening, continuous infinite events. Okay, so for example, this could be a space with temperature and pressure, or you could have two thermocouples. This could be simply a sampling between T1 and T2. Okay, XY coordinates could mean T1 and T2. And each one of these points is a possible value of T1 versus a possible value of T2. So in that case, we are giving something like P of T1, T2. Now, there is a small problem here, which is what we try to address through this probability density function rather than a probability mass function. So the problem is this. The problem is, let's just take a 1D case. Okay, so let's say there is some, I have given the example of rainfall, but let's take the example of temperature. Let's say temperature varies between 10 and 20. And we have to give a probability for each event. Remember, we are trying to distribute this entire probability, which sums up to 1 between these values. Now, there are infinite points here, right? So obviously, each of them, regardless of what you do, each of them is likely. So you will basically get 0. When you divide 1 divided by infinity, you are going to get 0 as the likelihood of each point. So you cannot ever say what is the likelihood of getting a temperature of 10.123456, etc. What, however, we can do is give probability for a range, or we can give the density of probability. Okay, just like if I want the mass of a point within a solid body, I can't give it, but I can give density of a solid point because that's mass per unit volume. Now you can think of probability density as a non-uniformly dense body. Okay, it starts here, ends here, and it tells you in each place how dense, how much more likely it is. So I'll show this via a histogram later on. But the reason why we define probability this way, now notice, P of x multiplied by dx is actually the unit probability. What it means is, instead of giving probability for a number, we give probability for a range. As an example, let's take a finite range and then we will reduce it to infinitesimal range. Okay. So for example, I will take a finite range. I will say, what is the probability that rainfall lies between 10 and 20 mm? Okay. Or I can say, what is the probability that temperature lies between 10 and 20 degrees centigrade? Now for that, you actually integrate in this entire area and you tell me the net probability. Now, what do you integrate? What you integrate is the density of the probability. So you say integral from 10 to 20 of P of x dx, where P of x is probability per unit temperature. Okay, that might not make much sense, but it is unit length in sample space, as I have written here, that we take. Now, what it means in finite terms is, what P of x does is, if you do multiply P of x by dx, it tells you the probability that X lies between X, a value X or capital X, sorry, and X plus Bx. So notice this is the random variable. These are the two values. Okay, so for example, P at 10 means what is the probability that the temperature lies between 10 and 10 plus some small dx or dt. Okay, obviously this number will go down to 0 as dt goes down to 0, but dp dx is a finite value. Okay, or p of x dx is actually a finite value. Okay, so what we do is we integrate between 10 to 20, not p of x dx. Integral of p of x dx between any two x is actually a finite value. Because using this and using analogy with what we did for discrete values, we now write what a probability density function for a continuous variable is and the conditions it has to satisfy. So the conditions it has to satisfy is that all possible states of x have to be included, as I said here. It is not necessary. So this is where it differs from discrete cases. P of x need not be less than or equal to 1. All we require is integral of p of x dx has to be equal to 1. Okay, you can imagine a function where individual values, individual densities are greater than 1, but it integrates actually to 1. So this is an important difference from before. So for example, we could think of a simple case, something like this. Let's say x is a variable, capital X is a variable that varies between 0 and 1 by 6. Okay, so x is a sample space such that 0 is less than x, less than 1 by 6. And I have p of x is simply 6. Okay. So you can notice this density is greater than 1. But when I integrate p of x dx between 0 and the entire sample space domain, you're still going to get 1. 6 times 1 by 6, you're going to get 1. So it's entirely possible for the probability density. Since it's a density, it can always be greater than 1. All it means is it's really, really dense. It's a relative quantity. What p of x talks about is how much more likely is it for me to find the random variable here in this space rather than somewhere else. That is all it really means. So you should not give direct value to p of x. You can only comparatively look at p of x versus somewhere else. So if it is higher, at that place, it's more likely for you to find the random variable. This is used very, very powerfully within quantum mechanics. And you will see this later on also. We will talk about this a little bit more when we come to the direct inverse problems in the next week. Now, a simple idea with which you can build this intuition is to make a histogram. So for example, when I say that temperature lies between 10 and 20, and temperature is a random variable, the way we would actually make measurements is we can't measure all the infinite temperatures. We will first say, okay, let me just count the number of times. Let's say I'm taking a thermocouple and at a particular point, I'm measuring the temperature. And I can now count the number of times that the temperature lay between 10 and 10.1. Okay. So maybe it was 5 times, then 10.1 and 10.2, maybe it was 6 times, etc., etc. Then I went till 19.9 to 20, and this was, let's say, 15 times. And now I take the total number of events, let's say this was 150, and find out the fraction, 5 by 150, 6 by 150, 15 by 150, and then draw a histogram. This is what is known as a normalized histogram, so that all of the fractions add up to 1. Now, of course, I could reduce this range further. Instead of making it 0.1, I could make it 0.05. Then I'll make it a little bit thinner, but it'll look a little bit more continuous. And as I keep on continuing this process, this starts looking like a smooth curve. Now, that is what a probability density function is. It is sort of the limit of taking infinitesimal widths and infinite measurements. And that is what looks like a histogram. So for example, something of this sort. So here the width is, let's say, something like 0.2. I think I took it, some variable that changes from minus infinity to plus infinity. You can hardly see anything here, but it starts looking like, you can imagine that the infinite limit of this histogram is what is the probability density function. Okay, so please try to, we will use the idea of probability density function in the next week, especially powerfully, but please try to get it into your concepts that ultimately you want this gap, which was 0.2 here, to go to dx as small as possible. And in that case, this height here would represent p of x, and integral of here, it's treated as a discrete variable, then p of x, sigma of p of x into delta x would be 1, but ideally you want integral of p of x dx is equal to 1. So we will move on to other ideas from probability in the next video, and see you in the next video. Thank you.